Now let's talk about the elements of propositional calculus. We've already been introduced to two of the elements, propositions. So we have the idea of a proposition, and we also were introduced to the basic idea of operators. So let's start with propositions. So as we just discussed in the previous tutorial, the idea of a proposition is essentially an assertion about the world that is the bearer of a truth value, true or false. So let's take the example of I have a headache. We could say that this proposition is a specific assertion about the condition that the world is in, and therefore it has an actual truth value. And we saw in our previous tutorial how we can combine two assertions about the world, I have a headache and I'm hungry, using some sort of connective. I'm using the English word and, which corresponds to a logical operator, which we will symbolize by the upside down V, or a rooftop symbol. So officially this is called a conjunction. So the conjunction essentially connects two propositions together, as we saw in the example, and because they're connected in a certain way that resembles a function, the function, or the conjunction in this case, takes two values, one from this side and one from this side, and it gives us an output based on what those values are. So the key feature of this is that H by itself is a proposition, and H and U, which stands for I have a headache and I'm hungry, is also a proposition. This logical form here can be represented more easily using variables instead of actual specific assertions about the world. So there's an important distinction that we want to make when it comes to propositions. Some propositions are constants, and this is an idea that comes from mathematics. Constants like pi or e, they have specific values. Other numbers like the number 2 or the number 5, those are specific values. And the same would be true of a propositional constant like I have a headache. It's an assertion about the world that's either true or false, and that is its truth value. But we could also, for convenience, we can represent propositions by variables. So when we're using constants, we normally use capital letters like H and capital U. But when we use variables, we typically use lowercase letters beginning with P, just a tradition or a convention. So we'll represent we'll represent the idea that this square could be filled in by any proposition using a variable P. So P basically stands for an empty slot that requires a proposition to go in it. There's another way we can think about propositions as well. We can also look at an individual proposition like H, which is a specific sort of, let's say, singular. Intuitively, it's a single assertion about the world, and it stands on its own. Another way to think about this, standing on its own idea informally, is H can't be broken down into further bits that still have a truth value. So if H stands for I have a headache, I ran out of space here. If H stands for I have a headache, then this cannot be further broken down into components that would still have a truth value. You can test this for yourself. So for instance, it does make sense to say true or false, I have a headache. That makes sense. But it does not make sense to say true or false, I have. In most contexts, that's an incomplete sentence, and so it doesn't actually have a truth value. Think about this, true or false, a headache. That is also an incomplete assertion. Incomplete assertions don't really claim anything about the condition that the world is in, and so they're not full propositions. So we can think about a proposition on the analogy of physics and chemistry and call those kind of propositions atomic. And the metaphor works there because an atom is the smallest unit of an element that is still recognizable as an element. You can still break it down into components like electrons and protons, but they won't be the so-called chemical elements anymore, right? They'll be bits and pieces that are used to construct elements. On the other hand, let's look at a proposition like H and U, which, as a reminder, stands for I have a headache and I'm hungry. This is also a proposition, but now you can see that it's a proposition that's built, as it were, from other propositions. So here's a proposition and here's a proposition, and these two propositions are joined together by one of our operators. We'll talk more about operators in a moment. So on the same analogy, we could call those kind of propositions molecular. And molecular propositions then are just going to be more complex propositions that are built out of smaller pieces. Now let's turn to this idea of operators. So we've already introduced one operator, the conjunction, which roughly corresponds to the English word and. In the system that we're developing, we are going to talk about 5 operators. We're going to build our system around 5 operators. We'll write the operators like this. And I'll tell you what these mean here in just a moment. So here are our 5 operators. So we have at the top of the list, not P. So this not symbol, this symbol right here, means, for instance, it's not the case that I have a headache. So if H stands for I have a headache, that's a proposition. And we can use negation, or we can negate that proposition by putting the negation sign out in front of it symbolically, but that corresponds to the English sentence, it's not the case that I have a headache, or more colloquially, I don't have a headache. So the thing to notice here is that even a proposition like I don't have a headache is in a sense molecular because it can be analyzed into a negation operation plus a simple assertion about the world, an atomic proposition. And that's how we want to think about it. We want to look at every assertion and ask, is this a proposition? If it is, then we want to identify whether it is atomic or molecular. If it's molecular, then we can analyze operators and possibly multiple smaller propositions out of that more complex molecular expression. So these 5 operators are negation. This one we've already introduced. It's conjunction. This is disjunction, which corresponds more or less to the English word or. We'll talk more about these in a moment. This is material implication. It corresponds more or less to if, then. And this symbol is equivalence. Material equivalence are the biconditional. So we have conditional and biconditional. Sometimes these operators go by various names. So we'll use equivalence. That's mostly the name. And it means basically the same as if and only if. So IFF is a abbreviation for if and only if. Now again, we will investigate the properties of these operators as we go forward here. But for the present discussion, we're introducing the various elements. So far we have propositions and operators. Now let's turn to another element here. We have groupers. Groupers enable us to group propositions together so they can serve various functions. So now let's talk about this for a moment. So in the previous example using conjunction, I made the point that the conjunction combines two propositions together to form a larger expression, a molecular expression, right? In our example, we looked at a molecular proposition that's built out of two atomic propositions, H and U, joined together by the operator AND, or conjunction. But if you look at this more abstract version of the logical form of this expression, which we could write with variables as P and Q, then we can make the point that whatever goes in this square on the left-hand side of this AND operator, and whatever goes in the triangle on the right-hand side of the AND operator, has to be a proposition. But it doesn't have to be any specific proposition. It doesn't have to be molecular or atomic or molecular. It can be anything that is actually a proposition. So for instance, if we think of this box on one side as containing a proposition, we could put a proposition in it like, I'm hungry and I have a headache and I'm hungry. And let's use capital S to stand for I'm sleepy. So look what we have here. We have the same logical form as we do in this original expression. The difference is that the box on the left-hand side contains a proposition that just happens to be more complex than a simple assertion like I have a headache. But this is a perfectly reasonable proposition in terms of its logical form, because the box that is on the left side of this operator has a proposition in it, and the triangle that is the right-hand side of this expression has a proposition in it. This happens to be a molecular proposition, and this is an atomic proposition. So now in terms of a schema, we could write that, and this is where the idea of groupers will come in handy. We could write that as P and Q. Notice this is a schema because it's variables, and S. Well, we could use R there. We can use anything as long as it's lowercase. So notice the logical form of this. We have everything in the square joined together by everything in the triangle using the operator conjunction. The groupers come in to play because they indicate to us what belongs together to go in the box on this side. And that idea can be extended as far as we wish. So for instance, we could have P and Q in the box on the left-hand side, and then in the right-hand side, what would go in the triangle might be R and S. Just like that. Notice, if we analyze this, we end up with the same logical form as we started. So this is the triangle right here. And the groupers help us identify what belongs in the slot on the right and the left-hand sides of this AND operator. So the whole idea behind groupers is they work to tell us what the operator operates on. So if you look at this simplest version of the schema, this operator operates on whatever proposition is in the box on the left and whatever proposition is in the triangle on the right. And it joins them together in such a way that it gives us a truth value depending upon what the truth value of those propositions in the square and the triangle are. So built into this idea of using groupers is the idea of scope. So scope just refers to what an operator operates on. So if we look at this expression, we can say that the scope of the operator AND is whatever proposition is in the box on the left and whatever proposition is in the triangle on the right. A little bit more formal way to write that is the variable P and Q, remembering that P is a variable that can contain anything. So P can contain a proposition of any degree of complexity. It could be atomic, like H, but P could also stand for something more complex like H and U. In any case, what we say about this is that the scope of this AND operator is going to be a proposition on the left-hand side and a proposition on the right-hand side. So the idea of scope, again, is just the idea of what an operator operates on. In our next tutorial, I'll introduce you to the notion of a well-formed formula, and then we will have all the ingredients we need to begin using truth tables to investigate the properties and characteristics of our 5 basic operators.